So good to see you here in very sunny Stockholm today for the Superhuman conference. And super happy to have you for this Owkin Superhuman podcast. And, we just wanted to kind of go with you about the future of longevity and how do you see the field. And first question, how actually do you see this field evolving and what's your angle on the big question of longevity?
Yeah, well, thank you. And it's wonderful to be here in now sunny Stockholm. I think we're on, I'd say, the somewhat extreme end of this field in that, we're building genetic medicines for health and longevity. So there's a lot of talk about, biohacking that in terms of getting into a sauna or a cold plunge. This is me or peptides.
Especially here.
Yeah. It's a readily accessible cold plunge. But this is meaningfully different than a genetic medicine. And the reason we're pursuing this is I don't think it's going to be possible to meaningfully improve health span or lifespan without a genetic medicine. I think that we have to upgrade our source code. You'll never take enough pills to fix this. And so that's what we're working on, building tools initially that would remove senescent cells, damaged cells, tools to build muscle without exercise and regenerate the body with genetic medicines, things that can stick around for a while.
But you're saying before, when we were discussing before the podcast, that the biggest challenge to do that will be delivery of these genetic medicines. And can you tell us what is the challenge around this? How are we going to be able to deliver new genes or fix the ones that are broken?
That is, I'd say, the Achilles heel of the field. And if you think about it from a history point of view, I mean, we've wanted to change DNA ever since we knew what the double helix looked like. And it wasn't really till the 90s that we got the first gene therapies that went into humans. But your body has a vested interest in not letting things change its DNA. And it thinks virus, it has a lot of defenses. And so the first wave of these, you'd have to take the cells out of your body and change them when they were more or less defenseless in a dish and then put them back. And even today, things like CAR T therapies are largely based on that. And the in vivo gene therapies have been limited quite a bit in terms of what you could deliver and how many cells you could reach. And so I think that we're getting to a point where there's definitely genes we know that if we corrected them would fix something, where it's like a clear same monogenic disease. But to change a large percentage of the cells in your body is very difficult. And so that's why we've based everything we're doing on new classes of delivery technology.
And you're also saying that DNA in general is a great molecule because it's stable. You were giving the examples of mummies. Where DNA is still kind of okay compared to biologics like antibodies where things are, you need a cold chain and everything. So DNA maybe is your molecule, right? Because it's something that can be delivered at scale, even in countries where it's too hot or there's no other options.
Yeah. And I mean, it's actually not what got us into using DNA, but I think it's true. And for the most part, we still have to have a cold supply chain. Everything's a regulated space, but yeah, it's worth noting that the DNA doesn't fall apart at room temperature right away. And I mean, like our vector today is stable at a room temp for at least a month and in a simple refrigerator for a year of what we have actual stability data for. But the reason we actually started using DNA is that you can put a logic gate in it. So if you think about
what do you mean by logic gates?
Yeah. So think every nucleated cell in your body has the same genome, right? If I take some of your skin cells, they have the same DNA as a muscle cell. So same kind of things installed on their hard drive, if you will, but they're reading different apps. Skin cells read skin apps, muscle cells read muscle apps, and technically, you have like promoters and repressors, regulatory elements in your genome that dictate what genes are read where. And it might seem odd to think about it, but you have like antivirus programs, anti-cancer programs, and a cancerous cell, for example, knows it's cancerous. Not that it's sentient, but that it has a transcriptional fingerprint. You can tell what apps are running on it, and that it's damaged because of this. And so, if we deliver DNA, unlike say a simple biologic or even RNA, you can basically put elements into it that say, if you're senescent, kill yourself, or if you're a muscle cell, produce this thing. And so it could go into other cells and not cause harm.
You can really, it's an app store, as you were saying before.
Yeah.
It was a good
app store for the human body.
But however, we know we were like, so you're saying like, we're going to enhance the genome of everyone. We're going to be able to find a way, tissue by tissue somehow, and by a delivery system that works out. So your vision is that people will enhance the genome in a wide base.
Yeah, I think that's where this field's going. And I know it might seem crazy today, but when I got into the field, there were no approved gene or cell therapies. And now there's thousands in development. And the speed at which these tools have been developing is really quite phenomenal. And I think we're going to get to the point where it is actually cheaper to do things like that than it is to do it the old way. And a good example, I suppose it's a little bit of a tangent, but people would constantly freak out about the idea that only billionaires will get this or something like that. And
that's, I think, what people think.
yeah, well, it's also absurd. I don't remember whose quote it was. I should look this up because I love it and I say it a bunch. That, you know, billionaires are the ideal model organism for aging. That like if you have somebody who wants to pay to build a therapy, take it and report back, people should be cheering. This is like what
Guinea pigs.
yeah, why?
Yeah, good.
You don't worry about it.
Yeah.
But the reason I think that the whole idea is wrong is that there's like one weird overlap on the Venn diagram of what people like between like the payers, the physicians, the medical establishment, and the patient. And that's everyone wants to live healthy for a long time and die quick. And so if you look at like our treatment for building muscle, the frailty treatment, I think this, you know, we show it works. Your healthcare payer is going to pressure you to take it. It won't be walled off for someone who's really rich because they also would like for you to die a young, violent death at 150. You know, like crash a motorcycle. Like it is actually cheaper for the healthcare system. You're supposedly strong. And so I think people have this thing entirely backwards. They watch too much Black Mirror or something, and Dark Mirror, Black Mirror. Yeah. And that if you built a tool that meaningfully impacted the trajectory of health and disease, like the economic value alone is so significant that the people paying the bill are going to want you to take it. There's
a real incentive to do that scale. And you went, so just going to this vision finally. So if you really be super forward in like 100 years, and if you want to try to take some potential consumer angle, you would see people having their iPhone, doing their own sequence. Well, just drive us a bit to a Black Mirror episode right now.
Yeah.
In 100 years.
I do think, I know it's a bold statement, but I think in 100 years, what it means to be human won't be the same as it is today.
What will be to be human in 100 years?
We're going to effectively take control of our genetic fate. That these tools will get good enough that you could make somewhat arbitrary changes to your genome. And once that genie's out of the bottle, it is going to be very hard to get it back. And I think like right now, I mean, it took 10 years for me to, idea to the vein of the first patient when I was getting into this field. Now, yeah, you can type a gene sequence into your iPhone. It'll show up in the mail in a FedEx envelope.
What do you do? So you drive people for the podcast. So
yeah,
you're doing you're doing your gene sequence by your iPhone. You get printed somehow.
Yeah.
You get in your mailbox. So what do you do then?
Well,
you have it in your mailbox. So what?
Well, traditionally the way people made delivery vectors like this were viruses, and you're not going to be making that at home. You shouldn't.
Have you another particle and just like inject it? It's
a bad idea. But yeah, the idea of, so I gave a talk at NASA years ago about putting a DNA printer on a space station. So you could effectively send a treatment wirelessly to Mars or wherever. And if you're a physician who's on a space voyage, you can only carry so many drugs. But if you have the ability to make DNA, you can design a therapy on Earth and send it wirelessly and print it out and use the astronaut as a biofactory. And it sounded really crazy when I said that's a long time ago. But that's actually not that crazy. Like DNA printers exist today, and they're a little like the first, I think, office copiers, and that they don't work very well. But they do work.
We have a 3D printer at home, most of us.
Yeah.
Let's get a DNA printing at home.
Yeah, they're
absolutely.
And so if you think of like all the new delivery technologies, certainly ours, but a bunch of the LNPs, these are lipid-based particles, like little fat bubbles that are made on a microfluidic system. So basically a glorified syringe pump in a little microchip. and you could take the DNA out of your envelope. You could put it in.
Yeah, you would have like a little microchip, like a credit card size of things, and with microfluidic systems.
Yeah,
To be able to make your particle somehow.
Yeah, I think that. And I'm not advocating that people do this. I think there's a
What's been the last breakthrough, by the way, in what have been the last breakthrough in delivery technologies?
the stuff we're using.
Yeah, I mean, like, what's still a lipid systems? Has been new lipids to be used? What is in the field the last big breakthrough about gene therapy delivery systems?
Yeah, I think Oisín itself is really based on this new delivery technology called a proteolipid vehicle, and it's a little bit like, I mean, everyone's familiar with LNPs from, like, I think the Pfizer, Moderna, COVID vaccines were LNP
vaccine, yeah.
So it's a little fat bubble about the size of a virus. Those ones carry DNA or carry RNA usually, and the cells have to swallow them up, and they escape this, and that's how they work. The PLV is lipid-based also, but instead of being swallowed up by the cell, it has a little fusogen on the surface of it, a little peptide basically, and that allows it to fuse with the membrane of a cell and deliver the cargo right into the cytoplasm, into the middle of the cell. And this is very significant because it allows you to have the scalability elements of a lipid particle, but the ability to carry DNA and not just RNA, and to hit a huge amount.
It's the same size.
Same size, yeah.
Size. Okay.
You can tweak the sizes quite.
A virus, a lipid particles, but you can target it to actually deliver DNA and not only RNA.
Yeah.
That's the technology. That's amazing. When you speak about this, new DNA into particles that are lipid, there's the size of a virus that can be targeted specifically to certain tissue. That's the technology, and that can last long. But we understand how that will help for different tissue, like muscle, the liver. The liver is kind of really, but the brain, what's going to happen with the brain? It seems like a much harder one to target. So how are we going to regenerate the brain?
Yeah. Well, I'll get in over my head on the neurology and the brain aging guys, but you can administer things like PLVs into the CNS. They will transfect cells in the brain. You do have to put them there. So
so we're going to have a delivery system.
So like intrathecal or IVCT type injections.
I think the crowd intrathecal means we will like do in the back directly, like a lumbar puncture.
It's painful.
It's a bit painful.
And I think that as the field progresses, you'll probably see ones that don't need that anymore. Like certainly, there's versions of AAV virus that if you put into your vein will go into the CNS.
So maybe virus for the brain will still be better than lipids, nanoparticle.
It might be, yeah. I think that it's hard to predict how these things will progress.
Yeah.
The virus has this significant limitation in that your body knows what a virus is and it doesn't like it. And it's got like for as long as life's existed, it's been at war with the virus, from the microbe to us. And so you can usually only get away with that once.
But also the particles are loved by the liver.
Well, yeah.
So you have the other problem where they usually go in the liver pretty much.
That's a really good point. I'm glad you brought that up. So this LNPs, like if you put an LNP in your eyeball, it will be in the liver in right away hours. It permanently traffics there. Yeah. The PLVs don't though. It's actually due to like the kind of structural composition of them, what they're made of, the lipids and the cholesterol. So a PLV, if you put it in your arm, it'll stay in your arm. You can actually make versions that you can put in your vein, and the liver won't be touched because its entry characteristics are different and what's made of are different. And so that's a really good point. But there's obviously a ton of work people are doing on all these things, trying to improve and alter their body. Yeah, so I would guess that we'll have synthetic particles that reach the brain, on the horizon. That's not like instant.
5 years horizon, 10 years. That's key.
Yeah. I would think so. Although there's a big difference between someone showing something compelling in a lab or getting their big paper on it. And
in this fight, so there's the fight of the delivery, the particles, the virus. There's the fight of the structure of the DNA, the construct, and then there's the regulatory side. And so, how do you see which country is going to win there? I mean, you're obviously one of the world leader, and you're in the US, in Seattle. How US can compete against China, I don't really even want to talk about Europe.
Yeah.
I don't know, like Europe is like over-regulated and maybe not that forward in the system. So how do you see which country is going to win and why?
Yeah, that is something that I'm happy to say that the U.S. government does seem to be paying attention to at this point. But this is a real issue because as the technical barriers have dropped to be able to make these things, the regulatory ones become more significant. And I think that it took a decade to go from idea to clinic on the first therapy I made, and that's too long. Like if you, especially if you have like a disease that's terminal, you'll be dead before the phase one multiple times over. And so I think right now the focus has really been on China in particular, and everyone has talked a lot about the speed to clinic, which is significant. But I think there's actually an element that's less appreciated, and it's how can you iterate in an early clinical trial. And so it's, for those who aren't familiar with the process, developing medicines is probably the only real deep tech type disciplines where you're effectively not allowed to learn anything once you complete your IND enabling studies or your GLP toxicology studies. Like once that first patient's dosed, if you change something about the drug, it invalidates all the studies that got you permission to enter humans in the first place. And so you could go through your phase one, realize, oh, if I change this a bit, it would be better. And you're going to spend a couple of years at minimum redoing those old studies to get that in. And I think in China in particular, and I mean, Australia is a good example of this also to some extent in terms of effectively, privatizing early clinical trials. And you could,
so the more you privatize early clinical trials, the more you create competitions, the faster it goes, right? Very much.
Yeah, because you end up with like hospital-centric trials. They're not federal government mandated so much. They're local. You move fast. You get this early data.
Business, man. I want to go faster.
Right? Yeah, and then you come back to FDA with say phase 2 data, and you say, I've already shown or characterized the safety of the risk in a human. And
a lot of people do phase 1 in those, right? As you say, exactly.
Yeah, so I think that I mean it's a real threat to the biotech industry in the United States, I think, in that if you look at, a few years ago, no one licensed drugs out of China, right? That was like unheard of. Now, like
50% of I don't even remember.
It's significant. Yeah,
it
blew me away.
So the manufacturing technologies have adopted, have evolved. It's a good manufacturing as well.
Yeah, so they've been moving up the value chain from like the make an API or just like a raw material to like manufacture R&D therapies to actual drugs and now to developing them. And if you put this critical step of the early clinical learning entirely in that world, we'll pay a price for it. And that like you effectively could not be working on a new modality and not be doing it there because you'd be paying a penalty of years on a handicap for it. And that is going to have an impact. And I think in general, like the US and Europe are likely to not ever get quite as comfortable with the risk-reward balance that China is today, but they could certainly be more Australia-like. And there's things about this that like I think deserve real merit. That risk-reward is something that I think at some point becomes an individual decision more than like I should be the arbiter of what goes in my body. Like if I have especially a terminal diagnosis. I shouldn't be waiting for ethics to sign off on what I'm doing. It's I mean, think about it, it's weird.
No, yeah, I agree with this. It's same for privacy of data. People don't share. We don't have enough data. I mean, so I agree. If people should choose where the data could become,
yeah, I mean,
used for.
You get a prescription to kill yourself, quite literally, and you can't take something that's experimental because it might hurt you. And this true. Is an odd.
That's a big paradigm to change. So 3 more formal questions. So we're still speaking about delivering new DNA, building, repairing, breaking genes, but we don't really know what the DNA works. And we know 20% pretty much of the full DNA. There's so much non-coding that we don't know what we call dark DNA. I mean, DeepMind was working on this recently. So people could wonder, we're thinking about new technologies, delivery, but we don't even know how the DNA works. Where would you answer to people that wonder?
Well, it's a fair comment. So, I mean, think back when we first sequenced the human genome. There was a lot of people who thought that we were going to solve everything once we did, and B, strangely thought that okay, well, this part makes proteins, the rest must be junk, And I was like, it's got to be one of the more idiotic assessments ever. But like, it's like pop you open the hood of your car. And you're like, well, the wiper fluid goes there, the oil goes there, the rest are junk there. And you're like,
this is the non-coding DNA.
yeah. And so the non-coding DNA is like the control logic of life. And I mean, there is debris in the genome. It's not that like, we've been around for a while. It's got battle scars. But this control logic it turns out to be this very important part that we don't understand very well. And I think that, and this is probably what excites me the most about the field these days, is that we're looking at, I think the future of medicine is kind of a marriage of like synthetic biology and genetic medicine. And this is something where, despite all of the hype, I think is some ways unfounded about AI in the field, it really could make a difference.
I agree, but I feel like synthetic biology has beat a little down fashion.
Yeah.
Somehow I was like crazy like 10 years ago, and people are a little bit like letting it about, but I agree with you.
Yeah, and I mean, to be fair, like if you think of like the world of computer science, like every bug there was put by you or your friends. This is a man-made system. Like we can understand it, we can debug it. We don't understand these things about life. And one of the reasons I think it slows down AI on it is that there isn't the same kind of closed loop from it designing, it testing, it running a wet lab experiment and cycling back like it can with code, right? You can train it on GitHub. You can say, write me some code, and it can like write the code, run it, look at the code, and it can do that very fast. And in biology, like your mice only grow so fast, right?
Much harder. This is why in AI, in my field, people focus on chemistry because you have the same feedback loop.
Yeah,
coding, but in biology, it's much harder.
Yeah, and I do think
so much time.
Yeah, that's changing.
Okay, yeah.
But so I think it's getting better. But also, like if you look at some of the bigger models, like we do have a lot of bioinformatics data trained on like the genome of every creature we've sequenced, the transcriptomic data, protein expression data, and things that like the human brain can't really hold all those things in their head at once, but are actually relatively, I think, learnable to the models. And so I mean we've seen very significant improvements in the things we've built using AI enhancements to them. And so I think it's already there, but like anything else, it has a hype cycle that is divorced from reality.
And sorry, just talking about creators, few last questions. Is there creatures in the nature, animals, plants that we can learn things from to be able to accelerate this field of gene medicine? Yeah.
Well, this is like one of the challenges. Like there's lots of work done in like, fruit flies and worms and things like this. And we don't do this at Oisín, but one of the reasons it's hard is that like we're already very long lived. There's only one mammal that outlived.
Which one?
The bowhead whale.
The bowhead whale.
And there's bowhead whales swimming around with like harpoons lodged in them from the time Moby Dick was written, which is crazy to think about. They live at least a couple hundred years. And they have better DNA repair pathways. So they can respond to DNA damage better than we can. Which
I mean, they repair faster.
They have damage faster and more accurately from double-strand break repairs in particular. And so, one problem that it's if you make a mouse live 5 years, everyone's gonna think you're a god basically. But consider that most creatures will live and die before we get our first wrinkle. Like, so you can fix a lot of things, even in the mouse, that we already fixed. Our body already has solved effectively. So there's limits in what we can achieve by pulling these out. And I think there's a whole bunch of things that different creatures do better than us for this purpose so that we can pilfer them. I mean, I used to describe gene therapy as software piracy in the biologic world. They weren't developing things, they're just stealing them.
Okay.
And that's kind of, that's the state of the art for a long time.
That's super interesting. And just to finish maybe on you, and since because it's a longevity and you always wonder what people do. So first, you spoke about prevention versus, you always say that prevention is easier than, preventing DNA damage is easier than changing them or curating them or modifying them. So how can we prevent our DNA? And if the listener will wonder.
This is obviously tough. And the fundamental problem is that we don't understand biology that well, or aging for that matter. And so I make this distinction that we're not in the supplement or cold plunging business, or like we're on a very extreme end of this. And what I think really got us started were the senolytics, and actually those mice of the Mayo Clinic in the Buck, where the Inca mouse, where they could get rid of senescent cells, and show that a lot of the pathologies of age didn't really manifest themselves, and they lived longer and healthier. And so, one of the first things we built was a therapy to remove senescent cells. And ours, of course, is a genetic medicine and not the kind of thing that you can get your hands on really easily. But if you look at the early versions like dasatinib and quercetin, like these things, they're definitely carry risk with them. Like, not the kind of thing I suppose people should just be playing with all the time, but the ability to remove senescent cells, may well prevent damage in a way that would be easier now than waiting a decade to undo it. And I think that, like I said, we're on the far edge of what's possible and what might. It's hard to say what's advisable. And this is, I guess, maybe I put it this way, that a fundamental trade-off that you're looking at is that if you wait until there's a randomized controlled phase 3 trial of any one of these interventions, well, you might be dead, depending on how old you are, or you'll have incurred another several years, a minimum of damage that you try to fix. And so it's not, waiting to do something isn't a free lunch. And this is, you think about it conceptually, like even the way we regulate these things is that no one's really caring who's dying from the disease. They care if someone dies from a drug. And so it's why I think that people have to have more responsibility for what they're doing. And I have no doubt that if you look at this proliferation of bootleg peptides coming out from all over the world, that this is going to result in harm.
I absolutely agree. But I mean, anything at all, and I'm an oncologist by training, like anything you take, any pill has an effect, even supplements, and there's always a benefit risk to everything. But people always talk about benefits without talking about the ratio between this and the risk. And
and the regulators only look at the risk and not.
Do you feel that in this field, the more you know or the more deep you are, the less you do?
Yeah, I think there is a trend like that. That even people like me who are kind of the consummate, curious hacker, tend to be still a lot more circumspect about these things than the average person on, watching something on Twitter or Instagram or something.
And yourself, yesterday you were telling that what you really do is sports and exercise. And anything today that is actionable, right?
Oh yeah, it's maddening. It's definitely hard to beat regular exercise. You need to keep yourself in as good a shape as possible. It's actually why one of the first things we built was focused on frailty, and that
on what?
On frailty. So we're trying to build muscle without exercise, and because physical strength becomes everything as you age, right? It's not just injury and disease, it's your metabolic health, your cognitive function, quality of life.
Muscle is everything. People forget that muscle is the center of metabolism.
Because
metabolism happens in the muscles. People think about strength, but it's also just about having a better metabolism. But people really never talk about this.
Yeah, it is absolutely huge. It's why there's a concern if you lose a bunch of weight with, say, a GLP-1, that you lose lean muscle mass. Like why that matters, other than just not looking as good on the beach. It's because it can be hard to get it back. And I think that there's no path that goes to meaningful improvement in health span or lifespan that doesn't go through frailty first. Like no one wants to be 200 in a wheelchair or even 100 in a wheelchair.
Yeah.
And so the ability to preserve that is critical. And I think, it would be awesome if I could, take a shot and have a perfect beach body and perfect metabolic health and not do anything for it. But in practice, up in the mountains a lot. And I think it's good for the mind and good for the body.
And the very last question, what do we need, all of us, to be ready for the next era of genetic medicine? Do we need to do our own sequencing, or it's been commoditized, you can do your own sequencing like 30x at some app, sequencing.com, whatever, for $300?
Yeah.
But you're not doing it. Wow. Wait, what?
It sounds odd being in the... It's maybe because I spent a bunch of time in cybersecurity before I got into bio.
Okay.
So mostly, I think actually it's definitely valuable to be able to look at your genome, and not because necessarily you'll make sense of it today, but the tools that analyze it are getting far more accessible, for one, and at some point you may be able to make correlations that would be missed in a normal, by a physician treating you based on the symptoms. But I didn't want to have.
But you don't trust the technology.
Well, it's not that I didn't trust the technology; it's that I didn't want to have my genome escape into the wild.
That's more the risk.
And so I can order as a research thing, which I'll probably do at some point. But I would actually say here's an interesting example of how something that you wouldn't have expected a few years ago. I have friends now who basically take all their medical records, you can take your genome, you can put it on a little bot running locally, and you have this thing that all it does is it watches like medical journals get released, like PubMed or something like that, and it looks at new clinical trials, and all it's doing is saying, is there anything that came out today that might be relevant to a mutation I have, or might be relative to a problem I have? And that's something that like there's no physician on earth that's tracking it like that, because it's just for you, right? It's and you can feed all these things in, and be very careful with the cybersecurity element. Your operational security is important.
And that's the genome, because a lot of people are also talking about the epigenome. And to end this discussion, is the future based on genomic data, or the future, because we're going to have talks today about epigenomic clock is the key.
Yeah.
You need to reverse the epigenome. And what's your stance on this? And we're going to end the discussion on the stats. When in the world of omics will matter most?
Well, your genome's a piece of it, right? It's the blueprints for building the things that you need to build, and so and it's historically been immutable. And I said we're working to change this, but it's a key piece that I think you can very easily argue if a certain gene is broken, bad things happen, and certain mutations are associated with things very clearly. Others we don't, or they're complex polygenic things. With the epigenomic state, obviously matters a ton. Although I think the clocks and the tools we use for this are not actionable in a meaningful sense right now. Like
they're a surrogate marker.
A good question I says, if you could push back the hands of that clock, if I could just remove those exact methylation sites or change those epimarkers, would you be younger? And I think it's a fascinating question. Like, would you be younger? Like, if I just waved a wand, I solved some delivery problems, and I put this into your veins, and I just change those markers. Do you see a clinical change? And this is something I'd say we don't know.
I mean, the beauty of it is like there's millions of data points through this methylation island and whatever. So it does give you materials to do big models, big data. That's the beauty of it. In somehow it gives you like
and collecting them is good for this. And so there's definitely the boring element that if you take a sample at the same time, put it in two envelopes, they come back with two different readings, which is very disconcerting. But but I think in general, epigenetics matter, and it's and the fact that we're collecting this data is good. Although I think the average Instagrammer probably pays too much attention to it. It's not it's a deceptive, like it's something in the world of research I'd say more right now than actually actionable medicine.
Thank you so much. I think it was very super interesting talk. People probably have learned a lot, and have a great day. We're looking forward to your talk today.
Thanks for having me. It was super fun.